Hi, welcome to the last part of this tutorial on lower bounds for statistical inference in distributed and constrained settings with Jaydev Acharya and Himanshu Tyagi. I'm Clément Canan. For this fourth part, we will look at upper bounds and discuss some of the open directions. So if you've been through the first three parts of this tutorial, well, those were lower bounds, right? And one question is, of course, are they tight? And in particular, can we show that these upper bounds for learning that we either showed or evoked are tight, let's say under communication constraints or privacy? So just in that table, we've got lower bounds under communication constraints, the little weird icon that's broadcasting something, and under local privacy constraints, the I there. For discrete distributions, the delta k, discrete distributions over k elements. For Bernoulli products, the BD, d-dimensional under L2. And for the Gaussian case, d-dimensional Gaussian spherical. And here we're gonna show some of those upper bounds, specifically these two under communication constraints for discrete distributions and for Bernoulli products over the Boolean hypercube. We're also going to look at some upper bounds for testing, specifically under communication constraints. We're going to focus on that. There are analogous bounds for privacy. And we're going to look at identity testing for discrete distributions under the L1 distance, and mean testing, so testing the magnitude of the mean for Bernoulli product under the L2 distance. And also the hide-and-seek problem introduced in the third part of this tutorial by Himanshu, where just to so that you remember, the goal is to find one coordinate which is big. So the mean is mostly zeros, but it's one sparse, and there is one coordinate that has large mean, at least epsilon. And the goal is to find which one of the d coordinates is big. So we've got those three problems. So again, identity testing for discrete distributions over k elements, mean testing, testing if the mean has large L2 norm for product Bernoulli over the hypercube, and the hide-and-seek problem, and under communication constraints for private coin and public coin protocols. So the bounds are here. And just so that we're on the same page, that's 7 upper bounds to prove in roughly 30 minutes that we have. So we've got those 3 discrete distribution upper bounds under L1 loss, learning plus testing private coin and testing public coin. We've got 3 for Bernoulli product under L2 loss, learning the mean and then testing the mean for private coin and public coin. And the Bernoulli product hide-and-seek, find one large coordinate of the mean, for which we have basically 1 upper bound. So that seems a little bit daunting. Let's give some general techniques to prove upper bounds, since that can be useful. And in particular, let's do several of those upper bounds at once through one technique that we call simulate and infer. And the idea is that whatever constraints you have, so here communication constraints, so if under those communication constraints, given messages from, say, S users, the server could simulate exactly one sample from that unknown distribution P. The goal is just to simulate one sample from that P that the server doesn't know from the messages from S users. Then for whatever task you want to do that you can do with n centralized samples in the centralized setting, then you can now do with S times n centralized users. And I mean, this is pretty much a tautology. It's just if it takes S users to simulate one sample, if you take S times what you need, you can simulate enough samples to run the centralized algorithm on those. So that's a very simple idea. Hence the name simulate and infer. You simulate samples and then you do inference in the centralized setting. Let's see if that's actually possible and what that gives. So here's an easy theorem. For Bernoulli product over the d-dimensional hypercube, non-interactive private coin simulate and infer is possible where the number of users to generate one sample is d over L. So you've got dimension d, L bits per user. Well, if you've got d over L users, you can simulate exactly one sample from that unknown distribution. So let's see how. It's a warm-up, but it already has some nice implications. So, well, you've got D over L users, S is equal to D over L. So the first user is going to send the first L bits of their observation. So the first user has one draw from that unknown distribution P over the d-dimensional hypercube, has L bits to send. So just going to send the first L bits of their sample, first L coordinates. The second user is going to send the second L bits, etc., etc. And the F user will send the last L bits of their own sample. Then the server observes, well, all those messages, so S times blocks of L coordinates, and just concatenates them to obtain like that X tilde sample, which is just basically the first L bits from the first sample, the second block of L bits from the second sample, and the last will be the L bits, the last L bits from the S sample. So that's the d-dimensional plus or minus one vector. And it's pretty easy to see that since P is a product distribution, well, that X tilde is going to be distributed exactly according to P. That's all there is there. So given D over L users, you can simulate one sample from that unknown P. Exactly. So that seems like pretty obvious. What are the corollaries? Well, the first corollary is that you can do non-interactive private con mean estimation under the L2 loss with D square over epsilon square L users. And that is the upper bound we wanted to show. And the proof is really simple. It's just in the centralized setting, the sample complexity to do mean estimation in L2 is D over epsilon square. You just take the empirical mean, that works. So, well, that times D over L is exactly what we wanted. So that's the first corollary. The second is, well, all of that is going to be private coin so far, just because the simulated infer is private coin. While non-interactive private coin mean testing, where you want to check whether the mean of the unknown distribution is either 0 or has magnitude greater than epsilon, is now possible with d to the 3/2 over epsilon square L users. And again, it's simulate and infer. We just have to remember that the centralized sample complexity is square root d of epsilon square. And again, this is not really hard to show. You just do the obvious thing. You take the squared L2 norm of the empirical mean, and via Chebyshev, you can show it works. So that's, if it's square root d of epsilon square in the centralized setting, you just multiply that by the d over L we've just seen, and you get exactly what we wanted. A third corollary. If you want to do hide and seek, well, now you can do that non-interactively with private con protocol with d log d over epsilon square L samples. And again, it's simulate and infer. You just have to remember that in the centralized setting, hide and seek is just log d over epsilon square. That's tight. And the idea is, well, you try to, if you don't have any constraints and you've got all the observations, what you want to do is find one coordinate that has large mean, just estimate each coordinate up to, I don't know, epsilon over 2. That takes 1 over epsilon square per coordinate times log d for a union bound over all d coordinates. And that gives you the log d over epsilon square you wanted. And now, well, you've got those constraints, but you can just do simulate and infer with a blow-up factor of d over L, and you're done. So these are 3 upper bounds that we just got in very little time via simulate and infer. Let's do 2 more. Those were for the Bernoulli product case, which simulate and infer was remarkably simple. Well, it turns out you can also do the simulate and infer kind of argument for discrete distributions. Specifically, we have a result that says that for discrete distributions over k elements, non-interactive private coin simulate and infer is possible. And now S is k over 2 to the L. So just again, I'm not trying to cheat you of anything. If L is log k, then S becomes 1. And that makes sense because then the first user can just send their full observation. It's a log k bit thing to send. Okay, so we've up to constant k over 2 to the L, we should be good. How does that work? So okay, I lied a little bit. It's k over 2 to the L up to constant and in expectation, but the idea is the idea for the corollaries will be exactly the same. Now, how do we do this simulate and infer here? Well, let's just focus on the first case, which is 1 bit, L is equal to 1. So given that, let's just take 2k users. So S is equal to 2k, and let's just pair them. So there's going to be 2 users that are going to be 1 and 2. There, we pair them, then 3 and 4, we pair them, etc., etc. And by pair them, I mean they're just going to like send the same kind of message. They're just going to look, so the ith pair will just look at each of them are their own sample and just send the indicator bit of whether their sample is the ith element of the domain. So basically what's written on the slide. So again, we've got 2k users, that's k pairs, and each pair will monitor one element of the domain and just send the 1-bit indicator of like, is my sample falling on that element of the domain? Then the server gets those 2k bits, and the rule it's going to follow is if there is a unique index I such that the message coming from the odd user of the ith pair is 1, and on top of that, for that specific I, the even user of the ith pair is sent 0, then the server will output the index I. Otherwise, it just outputs a simple bot saying, sorry, I couldn't actually simulate anything. So again, each pair will send basically 2 bits, one pair user in the pair, and the server will just look at all those things and aggregate them this way. And if there's a unique I such that the first user of the pair sends 1, but also for that one, the second user of the pair sends 0, then the server outputs that I. So let's see why that could be a good idea. Well, let's condition on the server outputting something, so not outputting bot, not aborting. Then the probability that what the server outputs is equal to, say, element I is the expression that's at the bottom of the slide. Why? Well, we want to be sure that there's only one odd numbered user that sends 1, and this is the ith one, so that's pi times, for all the others, 1 minus pj, because they didn't, their sample didn't fall on the element they were monitoring. So that's the pi times the product 1 minus pj. Plus, we also want that for the even user of the ith pair, that person sends 0. So that's the 1 minus pi factor. And if you just write that down and like regroup things, you see that it's pi times something that doesn't depend on I. So that's just a normalization factor. That's great. That means that the probability that the server outputs element I, condition on outputting some element, is proportional to pi, which is exactly what we want. We can also show that, well, the probability that the server outputs an element and just doesn't abort is at least 1/4. It's like massaging a little bit the normalizing factor and like using some inequality in the middle. And we get that probability at least 1/4, the server will output something and not bot. So again, at that point, we have that, well, whenever the server outputs something, it outputs according to the right distribution, and also it will output something with non-negligible constant probability. So we're good. There's a caveat here, meaning that that inequality we use to lower bound this thing by 1/4 only holds if the distribution P is reasonable, meaning like not concentrated too much on one single element. And we can assume that with a simple trick using our private coin. Specifically, we can first go from domain K to domain 2K by just dividing by 2 the probability of each element and duplicating each element. That can be done with private coins, and we just do the factor 2 because we double the size of the domain. And doing that, we can make sure that the probability of each element is at most 1/2. Because even if it was 1 in the original distribution, now it's 1 divided by 2. So that's great. We just proved that the expected number of users you need to output one sample is at most 4K for the case where we have L is equal to 1. Now, how do we get further and get the general L case? Well, we are going to use the same idea, but first we're going to partition the support K in many sets of size 2 to the L minus 1. Why? Just because we've got L bits per user, so might as well use that. And the users will either send 0, sorry, I didn't observe the element I was monitoring, or they will send the index of their sample in the set they're monitoring. More specifically, again, we pair the users, and users 2i minus 1 and 2i will send 0 if their sample is outside Si, the set they're monitoring, or if their sample is inside Si, then each of these users will output the index of their sample inside that set. So you can check that you only need L bits to perform that message. And then the analysis is going to be the same as for the case L is equal to 1. And you can check that you will basically need up to constant on expectation K over 2 to the L users to generate one sample. So that's basically the gist of it. And that proves the theorem that we can do simulate and infer in a non-interactive private coin way under communication constraints with roughly a blow-up of K over 2 to the L. That's great. What does that mean? Well, that means that we can do non-interactive private coin estimation under L1 loss, so learning a distribution with K square over epsilon square to the L users, which matches the lower bound that we claimed earlier in this tutorial. And to see why, well, you just combine what the theorem we just showed with the fact that the centralized sample complexity to learn an arbitrary discrete distribution of K elements is K over epsilon square. And again, this is kind of folklore. It's just you take the empirical distribution and that works. That's the first corollary. We also have for the testing case that, well, now doing non-interactive private coin identity testing under the L1 distance is possible with K to the 3/2 over epsilon squared to the L users. And again, this matches the lower bound that L given for that matches the lower bound. And the argument is quite simple again. It's just, well, the centralized sample complexity is square root K over epsilon square. So you just take square root K over epsilon square and you multiply that by the cost of simulate and infer. And that centralized upper bound instant, by the way, can be achieved in various ways. Maybe one of the simplest is just a chi-square type test, and you compute the expectation and variance. So these are pretty simple to obtain, almost immediate once you've got the simulate and infer subroutine. And that means we just proved 5 out of 7 upper bounds via distribution simulation, simulate and infer. And all were private coin non-interactive. So that just leaves us 2 upper bounds, the public coin upper bounds, so the white dice. I'm trying to be consistent there. And both will rely on some kind of dimensionality reduction. So for the private coin upper bound, we used simulate and infer. For the public coin ones, we're going to use the public randomness to project our non-distribution to a lower dimensional random subspace. So that's a kind of dimensionality reduction we call domain compression. So this might be a little bit abstract for now. So let's see an example again, starting with the product Bernoulli, so product distributions over the hypercube. So I claim that for this class, non-interactive public coin mean testing under L2 loss is possible with D over epsilon square root L users. So again, just sanity check. This is an improvement over the private coin, which was D to the 3/2 over L epsilon square. Think of L is equal to 1, that's an improvement by a factor square root D. This also makes sense because if L is equal to D, then the blow-up factor goes away. And yes, indeed it should be, because then you can actually send your full sample. You just have D bits after all. And yeah, so let's see how that's possible. And the idea is, so we've got all those users and they all have common randomness they can use. So they're just going to use them in some basic way. They're just going to select a uniformly random vector Z, which is a +1 - 1 vector, D-dimensional. And then each user, once they've got that, we'll just look at the observation. So user I as xi, it's a d-dimensional vector, and just going to compute instead xi prime, which is the component-wise multiplication of xi with z. So I've got my observation xi, and the jth coordinate of xi, xij, I replace it with zj times xij. So, okay. Now it's easy to see that condition on z, the new mean is preserved. So the L2 square norm of the mean, if it was mu, if the mean was mu before and had like L2 norm squared, I don't know, epsilon, then the new thing, epsilon square, then the new thing has still L2 square norm, at least epsilon square. So that's good. That's just because we just multiply this coordinate by either +1 or -1, so that doesn't change the magnitude. But we'll see that actually can help quite a little bit. So the next step now that each user has their own xi prime is to partition the d coordinates in L groups, S1 through SL of the same size. Okay, and the user I will compute the indicator of whether the sum of the coordinates of their new sample xi prime. So I take my xi prime, I look at the coordinate in the group ST, I sum that, and I check whether it's greater than 0 or less than 0, and I send the indicator of that. And so I've got L such groups, so I've got L such bits to send, and I've got L bits to send, so I can actually do this. At that point, the server will get n IID samples from some distribution PZ on +1 - 1 to the L, because each user sends L bits, and there are n users. So, okay, but why is this good? Why does that make sense? Well, first, that PZ, once you fix Z, condition on Z, PZ is a product distribution over +1 - 1 to the L. Why? It's just you had a product distribution, you partitioned the coordinates, and you just looked independently at those subgroups of coordinates to compute each of the L bits. This is still a product distribution. It's also easy to see that if P had mean 0, then PZ has mean 0. It's not the same 0. One of them was d-dimensional 0, and the new one is L-dimensional 0, but this is still 0. Now, the maybe more tricky part is that if the original distribution P had mean mu, which had L2 norm at least epsilon, then the mean of that new distribution PZ, the mean UZ, will have L2 norm at least epsilon times square root L over D with constant probability over the choice of Z. So, which is what's written at the bottom. So basically, after doing this grouping and like computing a new sample, etc., over L bits, well, the mean is kind of preserved up to a factor square root L over D. Which again, just to check if L is equal to D, that factor disappears. That makes sense. So things seem reasonable so far. That last part, by the way, is not obvious. It's not like as obvious as the first one, the first two ones. Just to give a sketch, I'm going to unwave it a little bit, but it helps to think of each sum over a subset ST as basically a normal distribution. So we've got T, we've got L subsets. For each of them, basically a user will have, after summing the coordinates of that thing, some kind of norm and renormalizing appropriately, some normal distribution with a mean, which is what's written there, square root L over D times the sum of Zj times mu j. Mu j is the mean of the original P. Zj is the jth coordinate of that thing that the users selected using their public randomness. And the variance is 1. Which means that if, assuming that approximately approximate normality, that means that the tth bit of the sample is a Bernoulli with parameter which can be computed as the thing below, which is kind of what we want here. It's like omega of square root L over D times that sum over the subset ST of Zj mu j. So if you're on board with that, first we make that Gaussian approximation instead of just having a sum of IID things properly normalized. And then we get that parameter that's at least this thing. Then we can check that the mean vector of that new distribution satisfies, on expectation over the choice of z, satisfies an having an L2 norm squared at least up to some constant L over d times the original L2 norm squared of mu, which is good, because if that thing was at least epsilon squared, now we've got at least epsilon squared times L over d, which is what we want. That's the unwavering part. Proving that on expectation is not too hard, but now we would like that to happen with constant probability, and that can be shown. It's a little bit more technical, but we can show that with constant probability over the choice of z, which was chosen using the public randomness, then the mean of our new distribution, so the mean mu z, has L2 norm at least epsilon times square root L over d. And that's with constant probability. So then that's great, we're done. The server, whenever that happens, the server can do mean testing over +1 - 1 to the L of that new distribution PZ with a different distance parameter. Instead of epsilon, now it's epsilon times square root L over d, because that's the guarantee we have. But for that, how many samples are necessary? So how many users are necessary? Well, it's square root L, the new dimension, divided by epsilon prime squared. And if you just do the simplification, that gives exactly the d over epsilon square root L we wanted. So that's the sketch of the proof for this upper bound. Let's see how that goes for discrete distributions. So domain compression for discrete distribution is also possible. Actually, you can show that for discrete distributions over k elements, non-interactive public coin identity testing under the L1 distance is possible with d over epsilon square root 2 to the L samples. So the same sanity checks apply. Oh, sorry, that should be a k, not a d. The same sanity checks apply. If L becomes log k, then the things cancel. Yeah, sorry about that. It should be a k, not a d. And well, the idea will be kind of similar. We've got public randomness. So how do we use it? Well, the users have their common randomness. So they pick a common uniformly random hash function going from the domain of size k to the domain of size 2 to the L. And they all replace their observation xi by the hash of xi. And then they can send that because it's an L-bit string they can send. It lives in a domain of size 2 to the L, so L-bits suffice to send that. So the server will get an IID sample from some new distribution pH, it depends on the hash function, on a domain of size 2 to the L. The server also knows H because it knows the public randomness. So in particular, we had that reference distribution Q. We wanted to test whether P was equal to Q or P was far from Q in L1 distance. Well, the server can compute QH, which is the induced distribution via the same hash function. All that remains to do is basically test whether pH, we got samples from this thing, is equal to QH. Well, we know this thing, or is far from it. And well, what does that mean far here? So first of all, why is it a good thing to do again? Well, at that point, the server has an IID samples from this unknown distribution pH over domain size 2 to the L. It's also very easy to see that if P is equal to Q, then pH is equal to QH, because you apply the same hash to the distributions, essentially. Now, and that's the tricky part, you can also show that if P was far from Q in L1 distance, let's say L1 distance at least epsilon, then over the choice of the hash function, pH is still far from QH in L1 distance, but not epsilon. Now it's epsilon times that factor, that's square root 2 to the L over k. And that happens with constant probability. So again, this last part is not obvious. Similar, it's kind of the similar argument as it was for the Bernoulli product case. I'm going to unwave the argument for L1 distance. Proving the analogous statement for L2 distance, though, is a bit simpler. It would even suffice, but it's a bit less clean to state, and goes in three steps. First, you can check that the expectation of the L2 square distance over the choice of the hash function basically preserve the distance. The expected L2 square distance is up to constant factors, the same as the original L2 square distance between the original distributions. That's good. We would like that to happen with constant probability instead of just an expectation. So to do that, well, it's a bit tedious, but you can bound the variance of that L2 square distance. It's a random variable because it depends on the hash function that is selected uniformly at random. So it's a bit tedious because there are some dependencies you have to take care of, etc. But you can do it. And then once you've got a good bound for this variance, you apply Palais-Zygmunt's inequality, which is an anti-concentration inequality, and that tells you that things will go exactly as you want. So for the L1 statement, though, you will need a few more ingredients to get the analogous statement, but the L2 square statement will be a building block. So just to recap, at this point, we've shown that with constant probability, over the choice of the hash function that all the users can coordinate on, then the induced distribution PH is either equal to QH if P was equal to Q, or far from QH if P was far from Q. And that's good. The server can just do identity testing to that QH over a domain size 2 to the L with a different distance parameter, epsilon prime, which is, well, epsilon times the factor that we lose. And again, if you just do the algebra, the number of samples you need are square root 2 to the L, because square root domain size, over distance parameter square. But the distance parameter is that epsilon prime. So if you just replace things, you get the k over epsilon square square root 2 to the L that I claimed was enough. So that's all there is to it. In both cases, we used some sort of dimensional reduction, again, domain compression, to argue that over some randomized compression of the domain, the problem became easier because the domain has a smaller size. And even though the distance parameter has to shrink as well, we still win in that trade-off. And we get the optimal bound in both cases. And again, in both cases, we needed that public randomness so that the users could use the same domain compression, the same randomized mapping, and choose that ahead of time. Okay, so that's 7 upper bounds we proved. So mission accomplished, I guess. To summarize them, we proved upper bounds for estimation for both discrete distributions in the L1 distance and Bernoulli product distributions in the L2 distance for the mean for communication constraints. We also proved upper bounds, again, for communication constraints for discrete distributions and the Bernoulli products in L1 and L2 distance, respectively, as well as for the hide and seek problem for Bernoulli products, both for public coin and private coin protocols. And that matches the lower bounds that we've seen in the previous parts of the tutorial. So as a summary, overall, the tutorial was about techniques for proving lower bounds in both interactive and non-interactive settings for statistical estimation and testing under local constraints. This particular part of the tutorial was matching them with upper bounds and showing a few techniques that allow to get general upper bounds in, again, some kind of unified fashion. The plan was, after some introduction and setting the stage for the first talk, Jaidev gave some techniques for estimation lower bounds under constraints in both interactive and non-interactive settings. Then Imanshu did the complementary part, which was general frameworks to prove lower bounds for testing, hypothesis testing. And then there was this one, which was some upper bounds and like the discussion that's currently happening right now. Let's turn to some open problems and directions. First, I'd be happy to discuss open problems in detail during the conference, so during Fox, interactively. Feel free to reach out. either on the Slack channel. I'm not quite sure the modalities are going to be, but the Slack or Discord channel, or by email, or during the live session for this tutorial. Here are two open problems, just kind of general and maybe interesting. I hope you find them interesting. The first one is, well, we looked at local constraints, right? We've got those n users, or like n observations. Each of them has some constraint. Well, what if each of them had different constraints? So either you could go for completely different constraints, or just like some parameter that differs a little bit. So let's say different bandwidth constraints. Instead of having the same L everywhere, L bits to send, maybe the first user has L1, the second has L2, etc., up to like Ln. How does that go? What's the right trade-off then? Or different privacy requirements. Maybe the first user doesn't care that much about their privacy, so has like row set to 10. But the second one is a bit more careful about their data, so as row is equal to like 1/10. And the third one as, I don't know, row 3 is equal to 1/2, etc., etc. Or those on aggregate, those on aggregate that play into the final bound. The second open problem is maybe a bit more open-ended, is what about other types of constraints? So here, in this tutorial, we mostly talked about communication and local privacy. There are others. You could, as mentioned in the introduction, linear measurements, threshold measurements, even some types of memory constraints can be cast under that. Well, pick your favorite kind of constraints, or like anything that you think makes sense or would be interesting, and see if that actually it can be cast in that kind of things. So maybe malicious noise, Massar noise, or maybe like some kind of other type of noise, like erase your channel, or you name it, or like some kind of specific measurements. So I mentioned linear measurements, but maybe you can only do a threshold. Maybe you can only get something that is rounded to the nearest integer after you add some noise. There are many, many possible things that actually are local constraints here. And finally, before concluding, I'd like to remind you that there's a detailed bibliography for the things we've talked in this tutorial that is maintained at this URL. So first of all, please check it out. If you feel we're missing something, let us know. That's the beauty of it being a web page. We can actually update it in case we missed anything. And on that, I'm going to leave this. And well, thank you, and hope you enjoyed the tutorial.